Unit 1.1, constant velocity. Let's suppose that I am at Verona Area High School in its new location, and I'd like to walk to Subway. To do this, I'd first have to walk north to Verona Avenue, and then I'd walk almost due east to get to Subway. Now, in this scenario, I've got what I'm going to call an origin or a starting point, or a place that I'm going to use as my definition of the center of the universe. I don't know if Verona Area High School is actually the center of the universe, but I'm going to call it that for the purposes of this. Now, the next thing I need is a scale, and we can see down at the bottom of the page that I've got 200 feet laid out. And I'm going to say that I'll walk north for about 800 feet. I am estimating here. Just marking it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 9.5. So let's say this is 950 feet. So the total distance that I would walk would be the 800 feet north plus 950 feet east, which is a total of 750 feet. But how far have I really traveled? If I were a bird from above, I would say that the distance I traveled is not 1,750 feet. In fact, it would be the hypotenuse of this triangle. It's not a perfectly right triangle, but I'm going to go ahead and use the Pythagorean theorem to estimate the length of this hypotenuse, or this almost hypotenuse. So I know that a squared plus b squared equals c squared. So I've got a, b, and c, and I'm going to go to my trusty calculator here. 800 squared plus 950 squared, and then I'll take the square root of that, and I get about 1,250 feet. So there's really two numbers here. There's the distance that I traveled. Distance is how many steps I got on my pedometer. And then there's also my displacement. And my displacement is the difference between my initial and final positions. Finally, please remember that we have an origin and we have an origin and we have a scale. And this really summarizes a lot of what we are going to study in this first section. When we define motion, we need a reference frame, and a reference frame includes an origin or a center and a scale. Now, very early in your mathematical career, you learned how to put things on a number line, and you learned that 0, sometimes called the origin, is going to be our center. Then when you draw a number line, you decide how far to space the lines. That would be our scale. And the other thing that we have in our reference frame is we have direction. Now, in math, we usually say that to the right is positive and to the left is negative. In physics, you don't have to do it that way. You can swap them around, but you do need to list which way is positive and which way is negative in your orientation. Let's jump into some vocabulary. Initial position, then, is our starting location. And in geometry, we would define it as a point. It's a zero-dimensional. It's just a point. The symbol for our starting location is x sub 0, and the unit that we'll measure it in is meters. This is the SI system, the Système International, in French, is meters, kilograms, and seconds. Okay, so final position is also a point in space. It's a final location. Its symbol is going to be just a plain X. This could also be instantaneous. location, instantaneous meaning at any given instant, and its unit will also be meters. Displacement we just defined. Displacement is the difference between starting location and final location. Now, displacement is a vector. And a vector means that it's got a distance to it, which was 1,250 feet, but it also has a direction. And the direction, if I look at north, south, east, west, a direction in the first quadrant would be northeast. So I'd say that my displacement from my origin, from Verona Area High School to Subway, would be 1,250 feet northeast of my original position. So again, we include a distance. Sometimes we'll use a fancy word for distance, which is magnitude. Magnitude just means amount. And we need a direction. That's what a vector is comprised of. It's comprised of a magnitude and a direction. The symbol for displacement will be delta x. And again, delta x will be the final position minus the initial position. And the unit then will still be meters. Okay, next, let's look at my average velocity let's look at my speed and my average velocity. My speed would be based on how far I walked, my 1,750 steps. So I walked north and then I walked east for my 1,750 steps. And if it took, let's see, how long would it take me to walk that far? Say it took me 10 minutes, just to keep my math easy. Then my speed would be 1,750 feet over 10 minutes, or 175 feet per minute. Now that's not the SI system, but it's something. That would be my speed. My velocity would be based on my displacement. So my velocity is going to be 1,250 feet divided by the 10 minutes. So again, speed is based on distance, velocity is based on displacement. So displacement was change in position over change, and now average velocity is going to be change in position over change in time. And the formula for it is going to be delta x divided by time. And the symbol for it is going to be a v. And this is also a vector quantity. So sometimes you'll see a little arrow on top of it to indicate that it's a vector, or sometimes you'll see it bolded when it's printed to indicate that it's a vector. The units will be meters per second. And then finally, speed is a scalar, meaning that we don't need direction included with speed. Back in middle school, you might have learned about speed equaling distance over time, or distance equals rate times time. This is the rate of change of distance. And speed is not a vector, so I did not bold it or put an arrow on top of it. And again, the unit is meters per second. Okay, so I'm going to do a little example here. I'm going to look at a simulation from a site called PHET. This is phet.colorado.edu, and I encourage you to go to the site on your own device. This particular simulation I'm about to look at is quite old. It was written in Java, but fortunately some smart programmers wrote a conversion program called Chirp, and it's converting the Java into something that the iPad can read. Okay, so here we've got a man standing on a number line. Notice he's at the origin. Notice that we have a direction. We have right is positive, left is negative. And what I'm going to do is I'm going to assign to him a velocity. I'll give him a velocity of, there we go, 2 meters per second. So when I press play, in 1 second, he'll go 2 meters. Oops, I was a little slow on my tapping there. And in another second, he will end up at 4 meters. Oops, well, I'm really slow here. Okay, so basically we can see his motion, and we can see how his motion is related to his position and velocity. Okay, now what I'm going to do is I'm going to look at his position as a function of time. And let's see, I'm going to put his velocity at about 2. Let's see how close I can get it. And I'm going to have him walk at 2 meters per second. The top graph is going to be a position time graph, and the bottom graph is going to be a velocity time graph. So he's walking at a constant speed of 2 meters per second, and I'll stop him when he gets to the end of the number line there. Oh, he stopped. Good. Okay, so we can see on this graph that his velocity was 2 meters per second. He had started at 0, and let's see, my scale is covered up. That's kind of a bummer. Let's see, this is like 1, 2, 3, 4, 5 seconds. So after 5 seconds, he had traveled from the origin to a position of 10 meters. During that time, look at his velocity graph. He traveled at 2 meters per second the entire time, and you can see that with this horizontal red line. We'll be coming back to these graphs multiple times. Okay, so if I wanted to indicate a reference frame in my notes, I could easily draw a number line. Right is positive, left is negative. And I could say, what if I had a car that started with an initial position of 2 meters? And then what would happen if that car moved to the left to a position of -3? Oops. So the car moved to the left. I would say that the displacement, and this is pretty easy because it's in a straight line, the displacement would be the final position minus the initial position. So that would be -3 minus 2, which is a displacement of -5. And that should make sense because look, 1, 2, 3, 4, 5. The object moved 5 units to the left. So when we graph motion in physics, as we saw in the little example, time goes on the x-axis, and we're going to title our graphs as x versus y. Therefore, we're going to make position versus time and velocity versus time graphs to describe the motion of an object. Also remember that the SI units for length and time are meters and seconds. We'll be working in meters and seconds. Let's go back to our simulation here, and let's do one more example then. I'm going to move this guy back. See if I can get him back to 0. Actually, I should probably just hit reset. I'll hit reset. There we go. Okay, and I'm going to get rid of the acceleration graph for now. Okay, so this time to make things a little more interesting, I'm going to start him at -4. And then I'm going to have him walk at a speed of 3 meters per second. Okay, I'm going to hit the playback button so we can see that again. So he's hanging out at -4, and now he's going to walk to the right at 3 meters per second. And again, we can see his position as a function of time in the blue and his velocity as a function of time in the red. Okay, so what we're able to do here is we are able to describe the motion of an object. The first equation we're looking at is displacement equals average velocity times time. And one thing I'd like you to practice doing is rearranging equations. For example, are you able to take delta x equals v bar delta t? This thing, by the way, means average. And are you able to solve for average velocity? I guess in my first go around here, I should be extra careful. So if I were solving for average velocity, I would divide both sides by time, and I would get that delta x over delta t equals v bar. And I know that I can turn that equation around. It's still the same equation. I can write v bar equals delta x over delta t. It's a good thing to be able to practice. Okay, next. I know that displacement is final position minus initial position, and here's how I would write that. In some textbooks, you'll see people write x sub f minus x sub I for final and initial. That is great. There's for final, there's initial. But the AP Physics 1 materials use a plain x and an x sub O. Okay, so now what I'm going to do is I'm going to practice making a substitution. I'm going to take this formula for displacement and I'm going to plug it in for delta x. So look at what happens. Instead of writing delta x, I'm going to write final minus initial position, or x minus x sub O, equals v bar delta t. And then I'm going to solve that equation for final position, otherwise known as x. To do that, I would add x sub O to both sides, and I end up with x equals x sub O plus v bar delta t, or you could write x equals v bar delta t plus x sub O. Okay, why? Why would you do that? Let's look at this exercise. Compare equation 4 to y equals mx plus b. Which variable represents slope? Which variable represents y-intercept? Okay. If I write y equals mx plus b below this equation, and if I go back to what I said here, that time goes on the x-axis and that we're going to make a position versus time graph. So this is time in seconds. This is position. The variable for position is x. Now this is weird because we usually, in math, put x on the horizontal axis. In physics, though, we're going to be graphing things the same way we did in math, but everything's going to represent an actual physical quantity, like position, like time, like velocity, like acceleration. What I see here is I see that slope is velocity, and y-intercept is initial position. So if I were to sketch on here, my y-intercept, otherwise known as b, is equal to initial position. And then my slope, which is rise over run, which is change in, usually we say change in y over change in x, but what is on the y-axis here? What's on the y-axis is change in position. What's on the x-axis? Change in time. And what we saw earlier is that change in position over change in time is average velocity. So here we see that slope is equal to average velocity. Okay, so let's do a practice exercise. A moving driver, not anticipating an accident, can apply the brakes fully in about 0.5 seconds. How far would a car driving down the freeway at 30 meters per second travel in this time. So I'm going to use my equation. No, I'm sorry. I'm not going to jump into my equation first. Here's what I'm going to do. I'm going to write down what I know. I have a time given here, 0.5 seconds. And I have a velocity given here. It's an average velocity, 30 meters per second. And I'm supposed to figure out how far. So I'm looking for delta x. So now I'm going to apply my formula because I see that I have those three variables. I want delta x. I know average velocity, and I know time. And 30 meters per second times 0.5 seconds, the seconds cancels out, and we get 15 meters. Let's try one more. A bicyclist travels at a steady 18 meters per second for 600 seconds, then at 6 meters per second for 1,200 seconds, and finally at 12 meters per second for 900 seconds along a straight level road. What is the average speed for the overall trip? Well, we know that average speed is delta x over delta t. So what I need here is I need the total displacement over the total time. And I'm going to have to do a little bit of math to figure that out. I'm going to start here with the 18 meters per second 18 meters per second times 600 seconds. Again, I'm using delta x equals v bar delta t. I'm plugging in v bar and I'm plugging in delta t. And 18 times 600 is 10,800 meters. Okay, so that's how far he goes in the first chunk. Then I'm going to do the next chunk. So I've got 6 meters per second for 1,200 seconds. (7,200 meters). And I like to write out the units. I'll do it even better on this last one here. I like to write out the formula in the units so that I really think about what I'm doing. 12 meters per 1 second times 900 seconds over 1. Look at what happens here. Seconds cancels, and I'm going to get meters as my unit, which is exactly what I want for displacement. So 12 times 900. 10,800 meters. Okay, so now to get average velocity for the whole trip, I'm going to take all of the distance. That's 10,800, the first one, plus 7,200, the second one, plus 10,800, the third one. And now I'm going to divide by the total time. That's 600 plus 1,200 plus 900. And I will get out my trusty calculator again. And I get, let's see, I get 10.7 meters per second. All right, let's jump in and try interpreting some graphs. Consider the position time graph for cyclists A and B. So let's look at this for a second. I'm actually going to color code these. Here's cyclist A. Starts at the origin, has a steeper slope. Here is cyclist B. Starts ahead of cyclist A, has a less steep slope, so it's going slower. So, do the cyclists start at the same point? No. Okay, so their initial position is, oops, I just mixed those up. Oh my goodness. This is why it's good to label. Their initial position is given by their y-intercept. So B is ahead. It has a higher y-intercept. At 7 seconds, which cyclist is ahead? Well, I don't know exactly where 7 is, but I know it's past 5. So I'm going to sketch this. And what I can see is that A is ahead of B. And I know that because it's higher on the vertical axis. If I go this way, this tells me position, and I can see that A has a higher position than B. Which cyclist is traveling faster at 3 seconds? Well, both of these cyclists have constant speeds, and A has a steeper slope. And therefore is faster. Are their velocities equal at any time? No. The slopes are different. What is happening at the intersection of lines A and B? Well, B started ahead of A. But A is traveling faster. And passes B. So A passes B right there at 5 seconds. Let's try another. Consider the position versus time graph below for cyclists A and B. Okay, so A looks the same, but B is starting way ahead of A and actually coming back in the opposite direction. How do I know this? Negative slope. That's a negative velocity. So A is going to be traveling to the right, like that, and B is traveling to the left, like that. How does the motion of cyclist A compare to that of the previous graph? It looks approximately the same. If I sketch A here, looks about the same. How does the motion of cyclist B compare? B is going slower. The slope is not as steep. And in the opposite direction. Oops. Which cyclist has the greater speed? A. It has a steeper absolute value of slope. What's happening at the intersection of A and B? A and B are passing in opposite directions. Which cyclist has traveled further in the first 5 seconds? Okay, so for, come on. So for cyclist A has traveled from that initial position to that final position. B has traveled from this initial position to the same final position in the first 5 seconds. But look which one is bigger. A is bigger. A has a larger change in position. See the vertical axis. All right. Thanks for hanging in there with me, and I will see you in class.